Okay, so today we are entering chapter 7, and this is all about hypothesis tests. Okay, and we talked about hypothesis tests maybe 2 weeks ago before the midterm, just very briefly, I think, right? Or I'm not imagining this, or okay. So we said that we start off with some kind of hypotheses. Okay, so we begin basically with a question or claim. About the population. Okay, and we have to turn this question or claim about the population into a hypothesis. Okay, so we must express this question or claim as a hypothesis. Okay, and in fact, actually, two of them. A pair of hypotheses that kind of work together. Okay, and so we will have a null hypothesis and we will have an alternative hypothesis. Okay, the null hypothesis H0 always has an equal sign. And then the alternative does not. Okay, and so essentially, whatever the question or claim is, we have to turn it into something where in one case we're saying the thing we're talking about, the thing in the population or the thing about our populations is that they're equally to each other, or it's equal to some value. Okay, and then the alternative says no, that can't be the case. Okay, and then we take a look at our data. Okay, and then we calculate a p-value, which is a probability. Okay, we calculate a p-value. Okay, and the p-value is a probability. So I'll say our p-value is equal to the probability of our data, resulting from pure chance and I have to say of our data, and I have to throw in this phrase, or something more extreme. Sorry. Okay, so it's the probability of our data resulting from pure chance if we assume that the null hypothesis is true. Okay, so we basically say, for argument's sake, let's assume that the null hypothesis is true. What is the probability that we get the data that we've observed? Okay, and then if the p-value turns out to be small, okay, we can conclude that that the assumption that the null hypothesis is true, we can conclude that that's wrong. Okay, so we can conclude that the null hypothesis is wrong. And on the other hand, if the p-value ends up being large, okay, we are unable to conclude that the null hypothesis is wrong. Okay. Note that I do not say we conclude that the null hypothesis is correct. Okay. Do not say we conclude that the null hypothesis is correct. We're just unable to conclude that it's wrong. Okay. Let's. This is just kind of the broad overview of hypothesis testing. Okay, we'll delve into specific examples with the t-test, and then I'm just going to kind of reiterate a lot of these same things to try to kind of drill our way of thinking into our heads here. Okay. Okay, so we're going to begin off with the t-test. Okay, and so and this is technically called the t-test for independent samples. Okay, and so the idea here is what we observe, our data, it comes from two samples. We've got sample 1. Sample 1 has size n1, has mean y bar 1, and standard deviation s1. Okay, and then we also have sample 2. Sample 2 has size n2, y bar 2, and standard deviation s2. Okay, they both come from respective populations. We got population 2 and population, which is just some large entity, and population 1, again, some just large unknown entity. All right. So sample 1 and sample 2 have been drawn from population 1 and population 2, and the question is based on what we see in our sample, can we conclude that population 1 and population 2 have different means? Okay. Okay, this is effectively the question that we are asking. Okay, and so in this case, when you perform a t-test, the question or claim that you're always kind of starting off with is, do these two populations have the same mean, or are the means of the populations different? Okay, so the kind of the quote-unquote question is, do these two populations have the same mean, or are they different? Okay, so some examples of questions could be, is do men and women have different blood pressures on average? Or do they have different whatever? You can just replace blood pressures with anything else, right? Different heights, different IQs, anything, okay? Different. So that's comparing one population to another, the means. Or do people who use Apple products, are they any different from people who use PC or Android or something like that? You could just ask kind of these questions about two different groups of people or things, whatever it might be, and we can just ask, well, we'll look at a sample of data. Can we make conclusions about the population here? Okay. So for the t-test, when we create our hypotheses, okay, so the hypotheses are going to look like this. So the null hypothesis is going to be written as the mean of population 1 is equal to the mean of population 2. Okay. Can also be written we can also write it this way, okay? Basically just using algebra to move terms around, we can basically say that the difference between them is 0, or is that there's no difference between the mean of population 1 and the mean of population 2. If we're effectively saying the same thing, okay? And then, so that's the null hypothesis. The null hypothesis says we're going to assume that the two populations have the same mean, okay? And then the alternative hypothesis says, no, the population means are actually different, okay? Or conversely, we can write it as doesn't equal 0. Okay? The alternatives can also, instead of a not equal sign, we'll talk about, so this one with the not equal sign, this is called a two-sided test or a non-directional test. Okay. Other possible alternatives are that mu1 is greater than mu2, or that mu1 is less than mu2. Okay, And these would be called one-sided tests or directional tests. Okay. And again, it can also be written as mu1 minus mu2 is greater than 0, or okay. So these are the hypotheses that we would write for the t-test. Okay. Okay, and so effectively, when we calculate our p-value, the line of thinking goes like this. We say we're gonna calculate the p-value. Okay, so then the next step is to get a p-value. Okay, and what we're saying is okay. You know, we look at our data, and then so again, from sample 1, so I'm going to just make up some stuff. So let's say okay, so we're looking at some rats, okay, rat brains, okay, and we exposed some to drugs, toluene, and then other rats we kept in a control environment. Okay, so this will be rat brain, and we're measuring norepinephrine concentration. Okay. So some kind of chemical in the rat brain. All right, and so our sample 1 and sample 2 have this data. So with there were 6 rats. On average, the norepinephrine concentration in the toluene group was 540.8, and there was a standard deviation of 66.1. And in the control group, we looked at 5 rats in the control group. Their average norepinephrine concentration was only 444.2, and there was a standard deviation of 69.6. Okay? So at first blush, when we just look at the data, it appears like toluene in this random experiment. It seems like the norepinephrine concentration of the toluene group is higher than that of the control group. It's almost 100 points higher. Okay, so you know what we see in our data is that you know, y bar 1 is greater than y bar 2. Okay, almost 100 points greater. Okay, and the true value is 540.8 minus 444.2. We get 96.6 points higher. Okay. Okay, so we're observing a difference of 96.6. Okay, and the question is, well, could this kind of difference actually just be a result of random chance? Okay, could the null hypothesis actually be true, and we just happen to get a random sample with a little bit high numbers over here and another random sample where the numbers were a little bit lower over here? That's effectively the question we want to know, right? So could the difference of 96.6 be just a result of random chance? Okay, and even this was like a difference of like a billion or whatever. Okay, the question is could it be a result of random chance? The answer is like yes. Okay, it's always technically possible for stuff to happen. Okay, the question is, well, if we assume that it's going to be random chance, then what's the probability that we get this result? Okay, and that's effectively what a p-value is. Okay, so when we get the p-value is, let's assume that the null hypothesis is true and any difference we observe is just a result of random chance. Okay, so we're going to basically say, for argument's sake, let's assume the null hypothesis is true, meaning that mu1 is equal to mu2. Okay, mu1 and mu2 being the norepinephrine concentration associated with all rats in the population of the toluene group, and mu2 would be the norepinephrine concentration of all rats in the population associated with the control group. Okay, so basically, so let's assume that the null hypothesis is true, meaning mu1 is equal to mu2, or that any concentration is the same for both groups, both populations. Okay, so let's assume that the null hypothesis is true. Then we ask, what is the probability that two random samples produce a difference of 96.6 points or more? Okay, and the answer to this question, that probability is our p-value. Okay, because the p-value is the probability of observing our data, or something more extreme, if we assume the null hypothesis is true. Okay, I'll write that again. Okay, it's like just one of those definitions that we have to learn. Okay, so the probability of observing our data something more extreme if we assume this is where we are. Okay, so we're saying, okay, we gathered our data. Sample 1, the average was 540.8. Sample 2, the average was only 444.2. We're getting a difference of almost 100 points. We're going to get the p-value, which goes under this assumption that says, okay, let's assume that that in the population, the means are actually equal. In the population, the mean of population 1 and the mean of population 2 are actually the same. What is the probability that random chance will end up giving us a sample where the difference we observe is 96.6? That's what we want to know. Okay? All right, and so the way we calculate this is effectively, it says if the null hypothesis is true, okay, then mu1 minus mu2 would equal 0, okay? And so that means we would expect y bar 1 minus y bar 2, we would expect that to equal what? We expect this to be close to 0, right? Okay. Does that make sense? If the populations have no difference in their population means, then when we take random samples, the random samples should also have close to no difference, right? Because of random chance, we're not expecting them to be equal to 0, but overall, we're expecting something close to 0, okay? So we get a sampling distribution. The sampling distribution of this quantity y bar minus y bar 2 is centered around 0, okay? So this is the sampling distribution y bar 1 minus y bar 2. It's centered at 0, okay? And the value we saw was 96.6. Okay, this is the value we saw. We want to know, well, what's the probability of getting a value of 96.6 or something more? This is what we want to know, okay? And technically, well, depending on what we're looking at, we also, our total answer will include both the upper and lower sides, because both a positive and a negative difference are of interest to us. Okay, so both a positive or a negative difference is interesting to us. Okay, so we want to know what's the probability that random chance would give us y bar 1 minus y bar 2 of 96.6 or more, or negative 96.6 or less. Okay. Does this make sense? Okay, this is what we want. Okay, and so at this point we're gonna basically get a z-score. Okay, but it's not a z-score because it's technically the t distribution, so we would get the distance from the mean expressed in standard deviations. Okay, so we would do 96.6 minus basically 0 divided by my standard deviation. Okay, standard deviation of the sampling distribution, which is known as the standard error. Okay, so the standard deviation of our sampling distribution, or the standard error, is the square root of s1 squared over n1 plus s2 squared over n2. Okay, so we're going to get this. Okay, so this is that. Okay, so just plugging in the values that we have. we have 66.1 squared over 6 plus 69.6 squared over 5. And I end up getting 41.195. Is that right? Here, I'll just punch this in. So 66.1 squared over 6 plus 69.6 squared over 5. And we'll take the square root of that. Yeah, 41.195. Okay. So my t-score ends up being 96.6 divided by 41.195. And I get 2.344. Okay? So my value ends up being about a little more than 2.34 standard deviations away from the mean. Okay? So does that seem, is that unusual to us, or is that not unusual? It's unusual, right? Our rule of thumb is that if it's more than 2 standard deviations away from the mean, it's unusual to us, okay? And so, you know, we're at 2.34 standard deviations, so, you know, it's a little bit unusual, okay? So it would be, so the results we get, the result where we're getting a 96.6 difference would seem unusual to us under the assumption that the populations actually have the same mean, okay? And so we can say, so there's 2 choices we have, okay? Well, and we actually haven't calculated the true p-value, and I'll show you how to get that. But our test statistic is 2.344. So our observed difference, of 96.6 is, you know, over 2 standard deviations away from the mean. Okay? So it's kind of unusual. So it's a little unusual, right? So it's a little unusual. Okay. So we have two choices, okay? So we have 2 possible conclusions. Okay? One is, this is unusual enough that we say that I don't think the difference the difference in the population is 0. Okay? Or we say it's a little strange, but not that weird. So I'm not ready to conclude that the respective populations are different. Okay, so 2 possible conclusions. One is our results are, quote, unusual enough, not even quote, just unusual enough for me to say that they are not a result of random chance alone. Okay. Thus, I conclude that the null hypothesis stating that mu1 is equal to mu2 is wrong. Okay? I reject the null, and I conclude that the alternative is true. Okay, that's one possible conclusion. The other possible conclusion is, we did not get a difference, there is a difference between y bar 1 and y bar 2. Okay. But this difference is not unusual enough for me to eliminate the chance or eliminate the possibility that it was a result of random chance, or for me to disregard? For me to disregard the possibility that it is a result of random chance. Okay? So I am unable to conclude that the null hypothesis is wrong. Okay? I do not reject the null hypothesis. Okay. Do these statements feel okay? Do you feel like you side more with one or the other?
So if they were greater than 2.3 test statistic, then we would use the first one.
Well, I mean, this is our test statistic, 2.344. Okay, and we just have to kind of decide, like, is this weird or is this not? Okay, and so to kind of help to guide us, we can use the T-table that tells us the associated probabilities with certain test statistics. Okay, so rather than just saying, it's over 2 standard deviations, let's go with that. We can say, okay, well, let's look up this value 2.34 in the T-table and try to make a conclusion. Okay, so we'll find the associated probability with the 2.34, and that's actually our p-value. Okay, so we will look up t equal to 2.344 in the T-table. Okay, so we have a few choices for degrees of freedom. We're going to use the approximation of n1 plus n2 minus 2. So we're going to have 6 plus 5 minus 2. We have 9 degrees of freedom. Okay, and we will see what the what 9 degrees of freedom say. Okay. So when we look at, when you go to the T-table, actually I might have a table here. Do I have one? No, I don't. Okay. Okay, well, do you have your reference tables with you guys? Okay, so if you look at the reference table, we're going to go to the row that says 9 degrees of freedom, okay? And I'm going to pull out a few, just a few values. I've got 2.150, 2.262, 2.398, and 2.821. Okay. And let's see, this is 0.03, 0.025, 0.02, and 0.01. Okay. So our value of 2.344 is in between there and there. Okay. And so according, if we use 9 degrees of freedom, and maybe we shouldn't, I don't know. If we use 9 degrees of freedom, then our corresponding, this is what this says, the upper tail probability. In our diagram, had 96.6 and negative 96.6. Okay, what this says is that this upper tail area is between 0.02 and 0.025. Okay, because 2.344 is in between this value and this value. That means the corresponding upper tail has to be in between 0.02 and 0.025. Is that okay? All right, and so what's the total area going to be in between? So the total area is between 0.04 and 0.05. Okay, and so we would write something like our p-value is between 0.04 and 0.05, or we could just write 0.04 is less than our p-value, which is less than 0.05. So we can say our p is in between 0.04 and 0.05 like that. Okay. Yes. Or question? No. No question. Okay. So then, let me just flip back to this side. It says, basically we're saying we can either conclude our results are unusual enough for me to say that they are not a result of random chance alone. Okay. Because the probability of us getting the results that we got from random chance alone, the probability of it happening from random chance is between 4 to 5%. So it happens about 4 to 5% of the time, and the question is, do you think, so we got these results, do you think the results we have was one of those unusual 4 to 5% of the time, or do you think it was part of the other 95, 96% of the time? And you got to make a choice, all right? You got to, if somebody says, okay, this is, you used up all of our lab's money for cutting up these rat brains and studying their norepinephrine, okay? What conclusion do you come to? Okay, you got to say, well, the p-value was between 4 and 5%, so I'm ready to say that they're unusual enough that the result I got wasn't a result of random chance. I'm going to conclude that toluene has an effect on norepinephrine concentration. Okay, or just as legitimately, you can say, well, it happens. The results I get can happen by random chance between 4 to 5% of the time. I'm not ready to say that what I got wasn't a result of random chance. So I have to conclude that, or I have to say I'm not ready to conclude that toluene affects norepinephrine concentration. Okay? And this is the challenge, or just this is part of statistics in that we're trying to make conclusions from limited data. We don't have all of the information available, and so we just have to make judgment calls based on what we know. Yeah.
Well, and what happened to like a sixth rat in the control group? I know it's small, but like, you know what I mean?
Yeah,
Like,
well, maybe it's expensive to do this thing, and so you could only afford to do it. It doesn't matter. It's okay that the
that's okay. That wouldn't skew it.
yeah, it doesn't. All right, the math takes care of it.
Okay.
I mean, it's
So I was just thinking like it's an extra rat in the.
yeah, but that's okay. You know, well, so technically, our degrees of freedom gets a little bit complicated when we have different sized things, and we're just kind of arbitrarily approximating the degrees of freedom with this. Okay, but it could change your things. Okay, but yeah, it's okay that we have different size samples. Okay, and even if you have a large thing, if you get 2,000 volunteers and you split 1,000 into one and 1,000 into other, some people are going to drop out of your study for one reason or another, and you might get like 950 in one and 970 in the other, and you might have a mismatch or something. That's okay. All right. Okay, so what do we conclude? Well, I don't know. So, but basically, if your p-value is small, you conclude this one. And over here, if your p-value is large, you conclude this. Okay? So that's actually probably worth its own slide. So we got a p-value between 4 and 5%, okay? And the guidelines are, if you believe that your p-value is small, then that means you reject the null hypothesis. Okay, and on the other hand, if your p-value is large, do not reject the null hypothesis. Okay. And so when you do t-tests, what you want to do is you want to draw kind of an arbitrary line in the sand that says, if my p-value ends up bigger than this, I'm going to say it's large. And if my p-value ends up smaller than this, I'm going to say it's small. Okay? And then and that line is called your significance level, or alpha. Okay? So prior to the test, you should choose basically a significance level. Alpha. Okay, this is an arbitrary line in the sand, or I'll just say an arbitrary line where basically if the p-value is greater than alpha, then you say it's large, and you do not reject the null hypothesis. And if the p-value ends up less than alpha, you say it's small, and you reject the null hypothesis. Okay? Life is probably a little bit more nuanced than this, okay, or I can say it is. But a lot of times if you're forced to make decisions, okay, forced to take your data and make a conclusion off of it, you're going to need some kind of criteria that says this is the spot where it's bigger than it, so I'm not going to reject, and it's smaller than it, so I'm going to reject, okay? and you choose this alpha, okay? And you as the researcher can choose whatever significance level you want. You can choose whatever alpha you want. Over the course of time, and to get published in journals and stuff like that, the kind of de facto standard most commonly used alpha is 5%. Okay, this is just somehow what has come to be. All right, and lately this has come under a lot of criticism because it's like, well, 5%, that seems arbitrary, and you'll see a lot of research articles getting published with p-values like 4.8%, 4.7%. There's this thing where it almost feels like people have maybe not even consciously done things, but have in their process of research inadvertently tried to just get their results just significant enough to get published, okay? And I don't know. It's something that's being discussed in the scientific community now, whether this is the appropriate thing to do or not. But there's a long history, and probably things will change over the next 10 years or so. But right now, this is the classical approach, and so just for whatever reason, a common or a very common choice of alpha is 5%. Okay, very common choice of alpha is 5%. And generally, if you want your study to get published, there's some pressure to say, like, you want, because studies generally aren't interesting if you don't reject the null, right? It's like, does eating green M&Ms only increase the risk of brain cancer? You do your study, oh, my results were insignificant, so I cannot conclude that eating green M&Ms increases the risk of brain cancer. That's not interesting. People aren't going to publish that, right? But if your results show that eating yellow M&Ms somehow increases the risk of something, then that could be of interest. Okay, now there might be problems with your study, but
So did they include the p-values in the study? Like,
yeah.
were to look at the
Yeah, if
study
you look at a study, almost always there's going to be a p-value somewhere in there, okay? And generally, the study, if they're trying to show that something is effective, the p-value would be less than 0.05. And if the purpose of the study is to show, or I don't know if the purpose, but if the conclusion of the study is to show that there was no significant difference between this thing and that thing, and one of our lab assignments, we're going to quote lab assignment, and you're going to read a research article where there's a p-value. The p-values are bigger than 0.05. Okay. Okay. So a very common choice of alpha is 5%, and again, this is it's an arbitrary value. It's kind of become the one that we have accepted as the norm. Okay, and the truth is it should be probably something around alpha. So what 5%. So why alpha equal to 0.05? 0.05 itself is arbitrary. But is pretty close to what it probably should be. Yes. I think 5% is a good value. Okay, I think 5% is a good value. There have been lots of studies about is 5% a good value, and they've done like basically using like they'll show you a bunch of images and that have been kind of randomly generated, and they say like try to pick out between the ones that were randomly generated and the ones that were not randomly generated, and when you ask humans to try to distinguish, they get it right about 5% of the time, something around there. So 5% is probably a good value, but exactly 5% is probably, it's a little bit arbitrary, okay? So it's probably a little bit higher, a little bit lower, but something around there. And so when your p-values end up very close to 5%, you probably want to look at it a little bit more closely rather than just saying for sure it works or for sure it doesn't work. It's kind of like, you know, in America, when you turn 18, you're considered an adult, okay? But, you know, is there something magical that happens between someone who's 17 years old and 364 days and someone who is 18 years old exactly, or 18 years old in 1 day? No, there's nothing magical that happens in that span of 24, 48 hours. But the age of whatever, adulthood, where you can start making decisions for yourself, probably should be something around that age. Maybe it's a little bit, it's different for everybody, but I think psychology has shown like your ability to think about the future and make decisions for yourself kind of develops, is fully developed around that time. And so it seems to make sense to hold people accountable when they're 18. But is 18 in of itself magical? No, but it should. So it's kind of like that. All right. Okay, so let's keep talking about this. I want to talk a little bit more about this alpha. Okay. So our significance level reflects our willingness to be wrong. Okay. So remember, if so our choice of alpha so remember, if our p-value ends up less than alpha, we're going to reject the null hypothesis, right? So if our p-value ends up being alpha, we say the p-value is small, and we say our data is unlikely to have been a result of random chance. Okay, and we say okay. And then and so we reject the null hypothesis. Okay, and we conclude that the null hypothesis is wrong, right? Okay. If our alpha is 5%, however, that means 5% of the time our p-value, like the null hypothesis could be correct, but our p-value just ends up less than 5%, right? So, because so let's see, we conclude the null hypothesis is wrong. But okay, you know, if alpha is equal to 5%, however, okay, that means even when the null hypothesis is true, our p-value by random chance ends up less than alpha with probability 0.05. Okay. Does that sentence make sense, or do we maybe have to think about it for a second? So, because basically, when we look at our data, we're just asking, what's the probability that we got this data by random chance, okay? And so that means, every now and then you're going to get a weird data thing, okay? Like where when you calculate the probability associated with the data, it's like only 2%, okay? And that's going to happen 2% of the time because the calculations say the probability of getting this data by random chance is only 2%. But that means you're going to get this data 2% of the time, okay? And so that means if your alpha is 5%, you're going to get data that causes you to reject the null hypothesis even when the null hypothesis is true, okay? And that's going to happen about 5% of the time. Okay, does that kind of make sense? Or what? No, 5% or less, okay? Yeah, 5% or less. So if our p-value is, less than alpha, we're going to reject the null hypothesis, okay? So this is going to happen 5% of the time where the null hypothesis is true, but we just get a weird data thing that causes us to reject the null hypothesis incorrectly, okay? I mean, we didn't do anything wrong other than trust the data, okay? And so this is called a type 1 error. Type 1 error is the null hypothesis is true, okay? But our data leads us to conclude that the null hypothesis is false. Okay? And so this is the wrong conclusion, right? This is our wrong. Okay, that's a type 1 error. So the probability of a type 1 error is equal to alpha, our choice of a significance level. This is the probability of making this error. Okay? So you might ask, well, why don't I just use alpha equal to like 1% or 0.5% or something, because I don't want to make this error, okay? Well, the flip side is making the other kind of error, okay? And so there's a type 2 error. And I know we creatively named these errors. So we call these type 1 errors and type 2 errors because when statistics was developing, there wasn't names for these, okay? There's probably more common names for these now, all right? So probability of type 2 error is the flip side, the other type of mistake, where the null hypothesis is false and it should be rejected. Okay, but either we don't have enough data or we were too cautious with our conclusions or whatever, we don't reject the null hypothesis, okay? But, you know, either our data leads us to conclude, leads us not to reject the null hypothesis, or we don't have enough data to reject the null hypothesis, or whatever, okay? But our data leads us not to reject the null hypothesis, okay? So again, this is also the wrong conclusion. Okay, and that's a type 2 error. Okay, and so if you decrease your alpha, you will be rejecting the null hypothesis less often, okay? But that's going to increase the risk of a type 2 error, okay? And so so we call the probability of a type 2 error beta, okay? So we have control over alpha, we don't really have control over beta, okay? So we can control alpha, okay? We can't really control beta. Okay, and decreasing alpha will increase beta. Okay. If we want to decrease beta, one way to do it is to increase alpha. Or if we don't want to increase alpha, but we still want to decrease beta, then we have to gather more data. Okay. So so decreasing alpha will increase beta. To decrease beta, we can either increase alpha, which increases type 1 error, or gather more data. Those are our options. Okay. Does this make sense? Type 1 error and type 2 error. So type 1 error, over time, we call this, we often will call this a false positive. And type 2 error, we'll often call this a false negative. But these are kind of associated, you know, more with like medical tests and things like that, and I think I don't know, somehow we became more like false positive and false negatives have entered kind of our vocabulary a little earlier than type 1 and type 2 errors have, but this is what we call them. Okay. Is this okay? All right, let's see. Okay, so let me do an example here. All right, so let's think of it like a criminal case, criminal court case. Okay. We say in court, we assume, or you are presumed innocent until proven guilty, right? So when we look at our, set up our hypotheses, we are going to put the null hypothesis as the one we assume, and then if there's enough data or evidence to reject the null, then we conclude the alternative. So because we assume innocence, our null hypothesis will be that the defendant is innocent, and the alternative is that the defendant is guilty, okay? And then data or evidence is presented, to try to support the alternative. Okay? So if there's not enough data, then the jury does not reject the null, okay? And they say the jury do not find we find the defendant not guilty, okay? Notice they don't say we find the defendant innocent, okay? They always say not guilty because we either reject or do not reject the null. We never actually say we have proven the null or we accept the null. We say we either reject the null or we don't reject the null, okay? So rejecting the null, or actually let me back up and we'll just say, okay, so in ideal situations, so the ideal situation is if the null hypothesis is true, okay, meaning the person is innocent. If the null hypothesis is true, then the jury concludes not guilty, okay, which means the jury does not reject the null hypothesis. Okay? Yes?
The data being presented, is that in our court case, the prosecutor, lawyer?
Yeah, it would basically the burden of proof falls on the prosecution, right? Like it's up to the prosecution to present evidence showing that the defendant is guilty, and if there's not enough evidence, then the case will just get dismissed. Okay. And then in the ideal situation, if the null hypothesis is false, okay, meaning that the defendant is guilty, then the jury concludes guilty. Okay, and so the jury rejects the null hypothesis. Okay, so null hypothesis is false. Ideally, we reject the null. Okay, and ideally, if the null is true, we do not reject the null. Okay, so this is the ideal situation. Okay, but again, in life where not all information is available to us, okay, sometimes we make mistakes. Okay, so mistakes. Okay, so what is a type 1 error? Type 1 error is a false positive. It's rejecting the null when the null is true. So what would that be?
He was innocent, but they found him guilty.
Right, okay, so type 1 error is rejecting the null, but in reality, the null is true. So in that case, that would be jury says guilty, but defendant is actually innocent. Okay. And then type 2 error would be what? Yeah, so this would be, not rejecting the null, but the null was actually false. But in reality, null is false, and so that is jury acquits, but the defendant is actually guilty. The defendant actually committed the crime. Okay. Now we don't want to make either of these mistakes, okay? Ideally we would always find not guilty when the defendant is innocent, and ideally we would always conclude guilty when the defendant is guilty. That's ideally what we want, and we don't want to make either of these types of mistakes. But if we had to, like, eventually we're going to make a mistake, and so if we had to decide on making mistakes, which one is the more, quote, preferable mistake? Type 2, right? I mean, well, at least this is how our court system is set up, right? We would rather make type 2 than type 1, so, or we would say type 1 error is worse than type 2 error. Again, we don't want to do either of these, but if we had to, we would say, you know, type 1 error is worse than type 2 error. Okay. And so, so would we want to use a big alpha or a small alpha? What do you guys think? So alpha is the probability of type 1 error, right? And so we've said type 1 error is worse than type 2, so we want to kind of reduce the probability of type 1 error. So do we want a big alpha or a small alpha? We would want a small alpha, okay? So type 1 error is worse than type 2 error, so we want to use a small alpha, okay? Or we want a small alpha because we don't want to increase beta. I mean, we don't want either of these mistakes, okay? But if we had to, we would rather have more type 2 errors and fewer type 1 errors, okay? And so we would rather have a small alpha and a larger beta than the other way around, okay? Okay. Now, of course, we wouldn't pick, and so when, and they say this in court. They don't say use a small alpha, but what do they tell the jury about a guilty what is that? Well, they have to make a unanimous decision, but they say you want to be sure beyond a reasonable doubt, right? Beyond a reasonable doubt. They don't want you to. They don't want juries to convict people based on a gut feeling or a hunch or something. They say beyond a reasonable doubt. And so, you know, that's how it goes. But we, you know, again, we don't want to make either type of mistake. You can imagine if there's a judge who says, I don't ever want to commit a type 1 error. Okay. Well, the only way the judge can be certain of never committing a type 1 error would be to let every single person go free, right? To say not guilty for every single person. That's the only way that the judge can be absolutely certain that they never convict someone incorrectly. Okay, but that would not make for a good judge. So if the judge never wants to reduce type 1 error, he can pick a small alpha, and that might mean letting some people go that maybe were actually guilty. And then on the other hand, you can have the flip side of the judge who says, I never want to let a guilty person off the hook, and he would have a high alpha, but then he would probably also be convicting a lot of innocent people. And so there's a balance there. Okay, why don't we take a small break here, and then we'll come back and continue our discussion.